All right, it's a great pleasure to introduce Justin. He'll be speaking on factorizable ABG equivalence and derived Satake.
Okay, thank you. So I never know if this is worth doing, but I should mention that this was very hastily prepared. So it's kind of pointless to say that because it's either an excuse if it goes badly or if it sounds like bragging if it goes well. So I just don't know. I wanted to tell you anyway. So um, all right. So first things first, I said I would talk about derived Satake, and I think that's kind of a logical place to start before moving on to ABG. See if the tracking working. Yeah, more or less. Okay. But actually, even before that, maybe I should do kind of a redux of Kevin's motivation from last time and just highlight the part that is relevant for ABG. Okay, so there's this kind of rough version of the local geometric equivalence conjecture. And again, it appeared in last week's talk. So there should be some categorical version, categories acted on by the loop group. Okay, and so this is some sort of DRAM analog of like smooth representations of the p-adic group in the usual local theory. And this is supposed to be approximately equivalent to sort of categories fibered over local systems on the punctured disk for the dual group. And so this is kind of a geometrization, DRAM version of kind of local Galois representations in the arithmetic setting. And everything here is kind of categorically one categorical level up. And so we should be considering DG categories fibered over this thing. A decent sort of proxy for this would just be modules over the monodal category of quasi-coherent sheaves. Now, I think Kevin presented it as instead sheaves of categories over local systems. And indeed, these are actually expected to be equivalent. So at present, it's only known that there's a fully faithful functor in one direction. This is due to Raskin. And it's expected to be an equivalence conjecturally, but this is not known. So I think at this level of detail, it probably doesn't matter too much. Maybe I'll work with this since it's slightly more concrete object. But yeah, so the key word here is that this statement that this is conjectured to be an equivalence is the conjecture that this free stack is one affine. So in any case, this is roughly what local geometric language is supposed to say. The reason it's not an exact equivalence is similar to the global setting when you state this kind of best hope version of the geometric language conjecture that involves quasi-co. There needs to be some kind of renormalization in order to make it literally true. And similarly here, you would need to modify the spectral side slightly in order to make this literally true. But I think maybe I'll talk a little bit more about these renormalization issues later. But for now, let's just take this as kind of a approximately true statement. And now this is supposed to satisfy many compatibilities. There are two that I actually want to use. And I think actually Kevin mentioned both of them last week. So one is that so they're both of the form like certain objects will match up. So one is that, if I have any space acted on by the loop group, its category D modules will have the structure of a categorical representation of the loop group. And kind of a canonical example of this would be the Epstein-Pressmanian. So its category of D modules is acted on by the loop group and belongs to this upper category here. And this is supposed to go to quasi-coherent sheaves on local systems on the punctured disk, on the non-punctured disk. Local systems on the non-punctured disk map to local systems on the punctured disk by restriction. And so this space maps to this space, and therefore this category is acted on by this category, or equivalently, you can think of it as kind of the structure sheaf of locsys on the non-punctured disk in this framework. It's worth pointing out this is, as a category, is very simple. It's just representations of G-check, but we're remembering the structure.
This equivalence, this injector equivalence true but known true for the non-BunG?
Yes. So that's the statement that the classifying stack is one of, which is
Yeah. Oh, okay.
yeah, that's right. The reason why this is hard for this stack is because this stack is extremely complicated. So it's not an Martin stack or anything like that. It's quite. Maybe I'll talk about it a bit more later. But it's a very, very complicated space in general. So all of this discussion that we've had so far about the Bezier-Kapnikov theory is really about a particular locus in here, the kind of locus of local systems with regular singularities, kind of meromorphic connection of pole of order at most one, and there this is somehow much more understandable. And so this kind of stuff doesn't really enter somehow. Okay, and then there's another compatibility, which again was mentioned last week. So this one will be involving both G and a Levy subgroup. So let's fix a parabolic and a Levy subgroup. Okay. And so this other compatibility will say following. So let's write it. So I can do a version, well, just take kind of input the group G times M here. Like this. And so then this other compatibility says, if I take D modules on the affine Grassmannian, sorry, what am I saying? Sorry. D modules on the loop group, and I take invariance for kind of loops into the unipotent radical of P times arcs into the Levy. Okay. So this is something we saw last time before. Yeah, sorry, not oh, so no. Sorry, I'm trying to, I keep making mistakes because I'm trying to kind of combine this with that compatibility, but I really just want this compatibility. Yes. So now we see this is, since the loops into the unipotent radical is normalized by loops into M, right? This is acted on one side by loops M and then on the other side by loops G. Okay, so this is some kind of affine version of the base affine space, parabolic version of that. And this maps to, it's supposed to go over to quasi-co, so sort of the structure sheaf, I wrote the structure sheaf on Lox's P check on the puncture disk. And this maps to both Lox's G check and Lox's M check via the inclusion of P and the kind of projection from P to M, which is sort of more canonical than that inclusion anyway. And so this is sort of the other compatibility. So this was stated last time, I guess, for the parabolic. Might as well say it for the parabolic. Okay. So these are kind of the two compatibilities that I want to take as my heuristic input here. Okay. And so then if I believe in this, I can then try to extract a kind of concrete equivalence of categories from these compatibilities. So if I have these two pairs of objects that are supposed to match up, in particular, Homs taken on one side should be equivalent to Homs taken on the other side, since this is supposed to be an equivalence of two categories. So it should look something like the following. Okay, so I'll take this compatibility upstairs that's sort of for G and M simultaneously, Okay, so I have this. This is supposed to match up with locus G check on the disk times locus M check on the disk. Map it to this thing. And again, local Langlands would predict this is approximately equivalent to the corresponding HOM taken in on the spectral side. Correctly. Okay. Okay, so we agree this is kind of what we get by applying this compatibility. These two.
You mean like D mods
Here?
Yeah.
Yeah.
Okay.
It means I'm like thinking of this as categorical representations of the loop groups. So it's modules for this monoidal category in their combination. Yeah. Okay, so this is sort of a prediction, right, of these compatibilities, and now this is actually an equivalence of infinity one categories, usual DG categories, and so this is much more concrete. And so this boils down to the following. So when I take HOM from GER-G equivariant with respect to the action of LG, I'm really taking invariance for the R group of G, right? And assuming all kind of dualities work out nicely, there's invariance versus co-invariance and stuff. But for things like the R group, that's not a problem. And then when I take, similarly, right, when I take HOM from D modules on the Grassmannian equivariant for loops M, that's going to be taking invariance for arcs into the levy here. So this HOM upstairs, okay, is D modules on the Grassmannian, invariant for loops into NP and arcs into M. See, so I'm taking invariance for the R group with respect to G and for G and M, right, on both sides. Okay, and then the spectral side then is, again, assuming everything is kind of nice and self-dual, which it will be, again, because these, especially because this category in particular is very simple. This is like bimodules for G check and M check. So this is going to be quasi-co on the corresponding fiber product of this with this over this. Okay, so all right, this is the same thing as this space, right? Times locus G check times M check on the puncture disk times locus P check on puncture disk. Reasonable. And so this is supposed to be the spectral side of this factorizable ABG equivalence. Okay, and now I can maybe say a few words about how to get from here to the ABG equivalence as we saw it previously. Okay. Okay, so for the left-hand side, this was already discussed in last week's talk. So if LG acts on some category C, for example, D modules on the Grassmannian, then there's a canonical equivalence between invariance for this group loops into NP, arcs into M, with invariance for the, let's see, how do you say this? So it's the unipotent radical of the corresponding parahoric. So what is the right notation for this? So what's the standard notation for a parahoric? I know equivalence is supposed to be I. Can I write like I sub p or something like that? That seems reasonable. Okay, so yeah, so like let's write it like in of I sub p. Sorry, not in, but just I sub p. Yeah, sorry. Okay, so this is the yeah. So sorry, it's just the full parahoric corresponding to p. So this is the thing, it's a subgroup of arcs G, and like if P is the Borel, this is the Iwahori subgroup. If P is the whole group, this is just arcs of G. So it's the subgroup of arcs of G such that when you reduce mod T, you get an element. And so this is kind of a categorical version of a theorem due to Bernstein. Again, it was discussed last week, at least in the case where P is a Borel. And this is the version that's worked with in ABG, working with the Borel case. But so for example, we'll just write it and P equals B. Of course, this is saying this time. And so their category on the geometric side is Iwahori equivariant sheaves on the crossbar, right? In particular, this is a nice thing because, I mean, one way to think about what the role of these subgroups, right, is that these two subgroups are both kind of different analogs of a parabolic subgroup of a loop group, right? There's sort of different things you could imagine would be analogous to a parabolic subgroup. Okay, these parahoric subgroups are sort of more often considered, I think, because they're just easier to handle somehow because they're, in the p-adic theory, because they're compact open subgroups here that corresponds to saying they're actually group schemes and not like in the group schemes. Okay, so this one has some advantages. On the other hand, this one has the advantage of having this factorization structure, which we're going to be exploiting a lot today. And so it's really crucial for us that we use this. Okay, but at least when we're kind of working at a single point, and so this parahoric subgroup makes sense, the invariant subcategories are equivalent anyway. Okay, so this equivalence is given by some kind of averaging procedure. It's sort of the thing that you would probably imagine it's given by, but again, this is some argument due to Bernstein. So this is the, automorphic ABG category. So that's good.
And the equivalence will not hold in families.
Well, yeah, because you're going to run into problems with even defining this parahoric thing in families, right? Like somehow if I have two copies of Iwahori at two different points and those points collide, the kind of natural limiting thing is actually not the Iwahori, but it's the thing where the Iwahori is like arcs into G, which send the closed point into B, right? And then if I sort of degenerate two copies of Iwahori at disjoint points to a single point, you're going to get the subgroup of arcs into G, which send like the second order neighborhood of the closed point into B. See, so that's actually the thing that fits naturally into a group scheme over X squared with Iwahori at the Iwahori times Iwahori on the disjoint locus. So this thing it doesn't factorize in that sense. So for this factorization business, we'll have to work with this thing, which is why I'm talking about it. Further questions about this? I can clarify.
I don't know what this is.
Which part?
Yeah, the C.
Oh, the C. This is it's some category acted on by LG. So an arbitrary DG category acted on by LG. I'm just saying this equivalence between invariance for this subgroup and this subgroup is completely general. It doesn't rely on any special features of D mod per G. So for example, if LG acts on some space and then this category D modules will be have this action of the loop group in this sense, and this equivalence will be valid in that setup. Yep. Or you could also take C, for example, to be Kac-Moody representation. You're also acting on something. This will be valid. Other questions about this? So that's the automorphic side. So then how do I relate this to the spectral side? This looks quite different from the spectral side of ABG, which I'll kind of remind you what that even was. And let's see that. So again, this was at least partially explained by Kevin. So if I choose a coordinate at the point X, so use a coordinate, then I get a map from the adjoint quotient. So I'll put checks on it to log_sys G-check on the punctured disk. And the way this works is, well, let's see. So I have a map from G-check to the space of G-check valued one forms on the punctured disk. Which sends an element of G to the one form like C times dt over T. So it's neuromorphic one form, with a pole of order 1 and the residue is C, right? And the claim is that, so remember, log_sys is G-check valued one forms modulo gauge action in the Duran setting. And so the claim is that when I then project to log_sys, so I mod out by the gauge action, this map is then equivariant for just the adjoint action of G-check acting on the Lie algebra. Okay, so the gauge action on these kind of neuromorphic one forms with exactly a pole of order 1 here corresponds to just the adjoint action of G-check on the Lie algebra. And so it's going to factor through a map like this. Okay, so this is kind of the basic mechanism that is going to relate spaces like this to spaces like this. And then sort of a position is that if I complete along the nilpotent cone, this maps isomorphically to the corresponding formal completion of log_sys along kind of local systems unipotent monodromy. And so if we're kind of only interested in these sort of connections with regular singularities with nilpotent monodromy or unipotent, so nilpotent log monodromy, right? And sort of deformations of these, then we can just work with this kind of much simpler adjoint quotient here. So this is sort of the piece, like I was saying, of log_sys that is most understandable. And this is the part that Bezukhadnikov's theories concerns. And so it's really once you go beyond this locus that log_sys starts to look much more kind of complicated and difficult to work with. When you work with kind of wild singularities, sort of going beyond the nilpotent cone, I mean, you'd still say some things about it, but then once you go beyond this regular singularities locus, it's really wild. But anyway, this is sort of all we need for Bezukhadnikov type applications, or at least what I'm going to talk about. So this is sort of, again, the kind of key thing to connect these. And so now this implies that this fiber product yeah. Okay. That allows me to identify this. Again, so basically I can replace yeah, and so I should have said, I guess there's sort of an analogous thing for Loxus P check here. So if I complete this along like Loxus in check, wherein is the unipotent radical of P check, this will be just the adjoint quotient of P check completed along the unipotent radical, nilpotent radical. So yeah, so anyway, this sort of thing gives you the following. So this is equivalent to this fiber product. Okay, and then this can be kind of further simplified just to the fiber product 0 fiber product over G check with the unipotent radical of P check modulo P check. You just sort of simplify this expression. Right, so sort of this copy of M check in the base here kind of cancels with the one here to give me just this nilpotent radical. And so sort of this G check times M check kind of cancels with that G check times M check, and I'm left with this. Yeah. Sorry? Well, that's the thing is like, this is already contained in the formal neighborhood of the trivial local system, because this derived fiber product, right? So this, if you like, you can think of this as sitting inside of P check times mod P check, right? Via the projection. And this actually sits inside of the formal completion at 0. It's this kind of derived intersection, right? So these are both linear subspaces of G check, and when you intersect them, you just get this DG scheme. So it's just this kind of, this looks like a kind of fat point basically. See? So if I just take at the level of like reduced classical schemes, this is just a point. Okay. And so it really is just some kind of DG thickening of the 0 locus inside P check mod P check. And I claim this is exactly the thing that appears on the spectral side of ABG. So I'll explain that. I think they don't say it in terms of derived algebraic geometry, but instead in terms of some extra gradings around and stuff, but just say it as follows. So this thing can also be written as follows. Let me just say the version for B, because that's what actually appears in ABG. I'm trying to relate it to what they said. So this is the version for the Borel, right? And so this is, you know, you can also write it with this. Right, it's the same thing. These two checks can cancel. So okay, and now this in check mod B check is exactly the Springer resolution mod G check. Kind of by the definition of the Springer resolution, right? The Springer resolution is like the induced thing from the like induced vector bundle with fiber in check on the flag variety, right? Via the action of B check on in check. So this quotient tautologically is the same thing as in check on B check. And so this is exactly the derived Springer fiber over 0 mod G check, which is precisely the thing that's considered in ABG. Again, I don't think maybe they don't say it in I forget exactly how they say it, but it's certainly equivalent to this. If you kind of take the version that doesn't have loop rotations and this extra grading. Okay, so this is how the big picture of geometric line lengths with this compatibility with parabolic induction recovers the ABG equivalence. Right. So I hope this was helpful to somebody as motivation. The thing that always confused me most, I think, when I was first learning about this stuff, was the precise relationship between the spectral side, kind of as we envision it in this version of local geometric line lengths, versus the kind of categories that Bezirkavnikov and his collaborators work with, right? And this is how you relate them. So I hope this is helpful. Okay. Questions about this before I proceed? Can you clarify? Okay, great. Yes, please. Sorry, which part? Up here? This map here, or it's this part. Oh, this, yes. So this, by definition, in the DRAM setup is, yeah, thank you, this is important. So it's one form, G-check valued one forms on the punctured disk, modulo the gauge action of loops. And this is, I mean, it's sort of technically difficult to define DRAM local systems in any other way than this, I guess I would say. Like on a global curve, right, you can define it as G-check bundles, which equipped with kind of a horizontal connection. But to say what is a horizontal connection on the punctured disk in algebraic geometry is this kind of painful thing. So there's this alternative model where you say any say it. So essentially this works because any G-check bundle on the punctured disk is trivial, is trivializable. Just I mean, for either the disk or the punctured disk, all G-check local systems trivialize. This is just by smoothness of G, right? So like any G-check bundle on the punctured disk extends to the formal disk, and then over the formal disk, you can trivialize it over the center, and then because it's just a G-check torsor over a point, and then you can extend that to a trivialization over the entire formal disk by smoothness. Okay, so any G-check bundle here trivializes, and then to the space of local systems is just going to be given by, well, connections on the trivial bundle, which are by definition given by G-check valued one forms, but then there's an equivalence relation, right, where two different connections can give rise to the same local system, and that equivalence relation is exactly represented by this gauge action. Okay, so this is, to me, is kind of the definition of this space. Try to define it other ways, but it's sort of much more complicated, and so this is the tautological projection. Other questions I can clarify? Okay, great. Yeah, I mean, this gauge equivalence thing is, I mean, I think if you think about physics, probably understand this much better intuitively, but for me, it's just kind of, by definition, it's the relation, right, that determines kind of when two connections determine equivalent local systems. That's kind of, so LG is sort of automorphisms of the trivial bundle on, sorry, that should be all LG check, of course, right? Automorphisms of the trivial bundle. Okay. Great, so onwards. Derived Satake. I promise them if I can even explain this reasonably, I think this will have been a success. Okay, so the automorphic side in derived Satake, and by the way, let me just say, to get derived Satake, get it from local GLC, you take d mod LG of d modules on the Grassmannian to itself, which say endomorphisms. So you just take this original compatibility of d modules on the Grassmannian goes to local systems on the non-punctured disk, and you take endomorphisms. Right, so this is then predicted to be approximately equivalent to endomorphisms over local systems on the punctured disk of local systems on the non-punctured disk. Okay. And so this is what we'll call the spherical Hecke category. I'm going to say it in more geometric terms. In more geometric terms, right? It's d modules on the Hecke stack. Right, so this is sort of an axisymmetrical way to write it, or you could write it like this. But this is the way that makes it clear. It's this double coset space, so that's why it's in the middle category, right? Convolution structure. And so this is the this is again predicted by sort of geometric lines to be monoidal. So derived Satake is supposed to give kind of a monoidal spectral version of this, or spectral decomposition of this category. And so we're supposed to get this thing on the bottom line. Let me kind of come back to this in a minute. So yeah. I mean, that's in some sense, again, if you deal with sort of like technical issues of duality and stuff like that, it's more or less tautological. This is kind of how convolutional double cosets works, right? And this thing is certainly a monoidal category, and it's also going to be important for us that it's also a factorization category. These two structures are compatible with one another. So this Hecke stack, right, just like the affine Grassmannian, it exists over the Ron space. It has this factorization structure, and the convolution on this groupoid is sort of manifestly compatible with this factorization structure. Everything takes place of the Ron space. And yeah, just because it's sort of constructed from loops and arcs in this way. Okay, so then how are we going to eventually get to a functor like this? So as a starting point, let me recall naive Satake. Okay, I don't really know if I like that term for it, but that's what it is. So the naive or classical Satake is a functor from rep G check to the spherical Hecke category. And it's monoidal, and it's also compatible with factorization. Now, let me say, if you take kind of the very classical equivalence, the geometric Satake equivalence at the level of abelian categories, it'll get you a monoidal functor like this sort of more or less automatically at the level of DG categories. Basically, because this category is the derived category of its part. So to extend the equivalence of abelian categories to a functor at the level of DG categories is something kind of formal. The right-hand side, though, is importantly not the derived category of its heart, and that's the reason why this is not an equivalence of DG categories, but it does give you an equivalence on the heart of the T structure. Okay. The other point is that it's a factorization functor, and this is something that does require some additional argument. It's not really written in this way in the original sources, but somehow the way that the functor is constructed makes it not too difficult to extend it to this factorization setting. So if you remember, geometric Satake is proved right by constructing some kind of viewing the heart of this spherical category as a Tanakian category. And in particular, you construct this fiber functor, which is given by global cohomology or something like that. And you have to prove that you have to construct also a symmetry constraint on the tensor structure here, right, in order to make it a symmetric monodal category and therefore Tanakian category. And the symmetry constraint comes from exactly this kind of factorization or fusion structure. Exactly comes from the fact that this thing lives over powers of the curve, right? So you use the fact that it's over x squared to kind of construct the symmetry constraint, right, and so on. And so somehow that's the fact that this is compatible with factorization is very closely related to this, just the construction of the functor in the first place. This can be dealt with. And oh yeah, maybe I should mention here, I'm thinking of rep G check as a monodal factorization category as well, so that you can think of this in one of two ways. One, it's a symmetric monodal category. As was explained a couple of weeks ago, there's some abstract procedure that attaches to any symmetric monodal category a factorization category, sort of commutative factorization categories. So it's like a commutative algebra in factorization categories. This is some abstract procedure. A little more geometrically, you could think of this as quasi-co of Loxus on the non-functional disk. Okay, and this thing has a factorization structure for sort of geometric reasons, right? Because it comes from the disk. Okay. Those factorization structures coincide. Okay. Great. So that's naive or classical Satake. The other major ingredient we need for the construction of the derived Satake functor is the geometric Casimir-Shaleka formula. We also mentioned last week. So far, this has been a lot of review of last week, but it wasn't recorded, so I think that's okay. Geometric Casimir-Shaleka says the following. So again, we have naive Satake. Okay, and then down here we have this Whittaker category of the Grassmannian. So remember, this was by definition, it was D modules on the Grassmannian, which satisfy an equivariance condition with respect to loops of n minus with some non-degenerate character put here. The role of n and n minus are swapped from last week. So for me, the Whittaker categories was with respect to n minus, and I'm using the positive part for on the other side. Anyway. Okay, so this is this Whittaker category of the affine Grassmannian. The spherical category certainly acts here, right, by virtue of it being this category of sheaves on the Grassmannian. And this category contains a canonical object, which is this Whittaker vacuum object that was mentioned last week. So there's a canonical functor here compatible with factorization, which is just given by acting on this canonical object. And because this object is a factorization algebra, this functor will be compatible with factorization as well. And geometric Casimir-Shaleka says that this composite functor is an equivalence. And so this is like the result of some calculations that are carried out in this paper by Frankel, Gaitsgory, and Bolonin. It's Whittaker patterns in the geometry of something. And you could already kind of interpret this as a derived version of Satake in some sense, right? Because it's an equivalence of DG categories that sort of kind of upgrades in some sense upgrades naive Satake, right?
What?
This is not monoidal. This is just an equivalence of factorization categories. Yeah, no, because this is a module for this category. So the statement is like this category acts on this category. This category contains a canonical object, and if I restrict along the naive Satake functor, this is a rank 1 free module for this symmetrical monoidal category. So it's not monoidal, and again, this is it's maybe not exactly what you would want from derived Satake, but it does in some sense correct the failure of the original naive Satake functor to be an equivalence. It does it in a maybe slightly unsatisfying way, because instead of enlarging the spectral category, right, to make it equivalent to this category, which sort of has more X, it somehow gets rid of the X on the automorphic side, right? So that now this thing is actually also the derived category of its heart and doesn't have these higher X's. So this thing is semi-simple, just like this. Okay, and this is enabled by replacing the spherical condition on one side with the Whittaker condition. Okay, which somehow these X's are coming from equivariant cohomology of G. So when you replace the spherical condition for G with the Whittaker condition, these X's go away. Yes. Which, sorry, what the Whittaker, what it means? Yeah, so there's this canonical character of loops in minus, which looks like the following. So you take loops in minus, you mod out by the derived subgroup. Okay, and then that's canonically sort of a, right, it is a sum over simple roots of copies of loops GA, right? Because it's this unipotent radical mod. Its derived subgroup is just a product of copies of GA. And then you do summation, and then you take residue. So in other words, you kind of extract the coefficient of T to the minus. So it's this character. Okay, and this is what I call psi. So it's non-degenerate in the sense that it's non-trivial on each of these factors, right, for each simple root. So non-degenerate means non-trivial on each of these factors. Okay.
So it's on each of these.
Non-trivial. Like on each of these factors, right? This is these copies of LGA. This is this kind of residue thing, which is a non-trivial character. Like non-trivial isn't just non-zero. Okay. Non-zero additive character. Yeah. And so then once I have this non-degenerate character, additive character of loops in minus, I can put this equivariance condition here by taking an Artin Schreier sheaf. So in the Durham setting that we're working in, this Artin Schreier sheaf is going to be the exponential D module here. So this thing is, it's a rank 1, it's a line bundle with a flat connection that's compatible with the group structure on GA. If I pull it back along the addition map for GA, it just decomposes as a box product of two copies of itself. So it makes sense to impose equivariance with respect to that thing, just like you would in usual representation theory for a character of an abelian group or something like that, right? And so this condition is the equivariance condition with respect to this character. So it's just, again, in usual representation theory, right? If I have some, say some abelian group acting on a vector space, right? And I have a one-dimensional representation of that abelian group, I can take the kind of invariance twisted by that one-dimensional representation. This is just the categorical version of that, okay? And it's something that comes up already in like representations of finite groups of Lie type and stuff. It's kind of classic construction there. Whittaker model, right? It's the term people use. Okay. So here's geometric Castle-Shaleka. Other questions about this one? All right. So the upshot is that we get this equivalence of factorization categories between rep2 check and then the Whittaker category of the Grossmanian. Okay, and then finally I get to the construction of the derived Satake functor, which is suggested by Gaitsgory and Lurie, some unpublished work from, I don't know, around 2006 or 2007, something like that. And this is never actually written down because, as we'll see, there are sort of technical problems that sort of obstruct actually fully carrying it out. But in any case, we can say what the functor is. So we'll start as follows. So I'll produce a functor from this category to rep G check. Okay. And this will, in fact, define an action of the spherical category on rep G check. Okay, so let's carry this out. So first of all, this is equivalent via Castleman-Shalaika. Castleman-Shalaika with the Whittaker category of the Grassmannian. Since with the spherical category. Okay, now the spherical category acts on this category, sheaves on the Grassmannian. And then I use Castleman-Shalaika again. In other words, all I'm saying is that this Castleman-Shalaika defines, yeah, I probably should have just said it this way. Castleman-Shalaika defines an action of, yeah, this is sort of a silly way to say it, an action of the spherical category on rep G check, compatible with factorization. Better to say it this way. Okay. So this is a really interesting kind of consequence of this Castleman-Shalaika picture, something that was really not clear before. So in the usual, or in the classical, naive Satake construction, you get a monoidal functor from rep G check to the spherical category. And this is saying something completely different. This is saying actually the spherical category acts on rep G check. I mean, I kind of already used it in the construction of Castleman-Shalaika to say that it acted on the Whittaker category, but then once you know the Whittaker category is equivalent to rep G check, you get an action of the spherical category on rep G check, compatible with factorization. So this is the observation. Yes. It's just like convolution or action, right? So this is something mod L plus G, therefore it's acted on by the spherical category. In other words, it's right. This is LG mod Whittaker on one side and L plus G on the other. This is the thing that acts universally, right, on L plus G invariance and anything acted on by LG. So I already used it here, right, to construct Castleman-Shalaika to say that the spherical category acts on the Whittaker category, right? And so then I'm saying once I know this functor is invertible, I actually get an action of this category and this category, right? That's the main upshot here. Okay. And now we're getting closer. So the way that I think Dennis and Jacob envisioned it was now that I have this action that's compatible with factorization, it's going to give me a functor from the spherical category to endomorphisms of rep G check, but compatible with a certain structure, which is the structure of factorization module over itself. So rep G check is a factorization category, therefore it's also a factorization module for itself, just like an associative algebra is a bimodule over itself. It's the same type of structure. And so the fact that this is compatible with factorization tells you that this action on rep G check commutes with this structure, and therefore it acts on this as a factorization module over itself. And then the idea is that this is, in fact expected to be equivalent is conjecturally with the category that appeared on the board over there. Which was supposed to be the spectral side of geometric Satake according to local geometric Langlands. Now, I mean, on the one hand, this is using something else. So let me just quickly remark on that. So conjecture is that there's a fully faithful functor from categories acted on by quasi-coeval cis, which is the spectral side of local geometric Langlands. This is supposed to embed fully faithfully into factorization modules for RepG check. Sort of another conjecture. And although it's not known, sort of it's in some sense, many kind of special cases of this are known. And in particular, it's known to be true for categories which are supported in a formal neighborhood of the trivial local system, which this one is exactly kind of representing the trivial local system. So in fact, this is okay. So this is proved in Raskin's thesis. Nonetheless, there are big technical problems with actually carrying out this strategy fully. So namely, this version of endomorphisms is sort of, say sort of has technical issues. So e.g., it's not clear that it actually factorizes. So again, if I'm at a single point, this is definitely going to be kind of the correct category. But if I'm trying to do things in families over the Ron space, taking this operation of taking endomorphisms, it's often a little bit problematic, right? Because I mean, endomorphisms is a right adjoint, so it like doesn't generally preserve colimits, and because of this, you're going to have some technical issues. So the strategy here is I constructed this functor. I'd like to say this functor is a functor of monoidal factorization categories, and somehow use that factorization structure to reduce the statement that it's an equivalence to a statement at a single point. That's kind of the strategy that you'd like to employ here. But because of this kind of technical problem of the fact that this thing is a bit unwieldy, it's not clear that it actually factorizes, it's unclear how to proceed from here, right? And to sort of make this into a factorization category and make this into an equivalence. A closely related issue is that in fact, the wiggly equal sign right on that board also intervenes here. So this is not expected to be an equivalence on the nose. There's supposed to be this extra renormalization step that occurs before you can actually prove that it's an equivalence. So one way of saying it is that there's a T structure on both sides that makes this into an equivalence on bounded below objects. But in order to make it into a literal equivalence, you have to kind of enlarge your category of compact objects. Again, not clear how to sort of carry out the necessary technical steps with this category. So that's kind of where I think Dennis and Jacob got stuck. So I'm going to explain my approach with Sam and how we kind of sidestep this. Questions about this?
We should take a break.
Oh, shoot. Is it already? Okay. Yeah.
I think it's a natural place.
Sure. Okay. Sounds good.
All right, so let's resume at 15 past.
Okay, good.
Also, can you make sure that the easy IP is on for the audio?
So we're starting again. Okay, back to it.
Yeah, sorry. I thought yeah, can we start?
Yeah, I was looking for it. All right. Good. Discuss more after. Okay, great. So I finished explaining this Gaitsgory construction of sort of a candidate for the derived Satake functor. Now I'm going to explain how to get past these technical problems and actually complete the strategy. So this is going to look kind of familiar if you were here last week. The idea is instead of trying to do this slightly awkward operation of taking endomorphisms of rep check as a factorization module over itself, we're going to replace this with a category of factorization modules for a certain factorization algebra. So look as follows. So if I sort of ignore the subscript in that monoidal functor that's written on the last board, the Gaitsgory construction gives me a monoidal factorization functor from the spherical category to endomorphisms of rep check. I can also write this, again, because rep check is nice and self-cool, as G-check bimodules. Okay. And so in particular here, again, because I'm just taking endomorphisms of this as kind of a plain DG category, not using this additional structure, there's no problem in making this into a monoidal factorization category. If you like, it's even commutative, right? It's sort of, well, as a factorization category, it's commutative. So one kind of small note of caution here is that I'm viewing G-check bimodules here as a monoidal factorization category. The factorization structure comes from just the tensor product, just usual tensor product of representations, right? Makes it into a symmetric monoidal category and therefore a factorization category. The monoidal structure comes from convolution of bimodules, right? Which is what corresponds to composition of endomorphisms. This is going to be monoidal as such, again, just because it came from a monoidal functor, an action of the spherical category on rep check. Okay, and this functor is, well, it's monoidal, and therefore the unit object in the spherical category, which is sort of the delta D module supported on the unit coset, right, is going to map to the monoidal unit in the right-hand side. So if I'm thinking about it as endomorphisms, it's the identity functor on rep check. And if I think about it as G-check bimodules, this is exactly the regular bimodule. Right? In other words, I'm thinking of this as like its functions on G-check viewed as a bimodule for G-check. Right? And this is the bimodule which, when I convolve with it, it does nothing. Right? Tensor with this thing and then take G-check invariance, you just get the original representation. This is the identity. Okay. And okay, so again, just by virtue of the fact that this functor was monoidal, it sends this monoidal unit to the monoidal unit. Okay. Now we're going to use this construction that was introduced in Frank's talk, which is when I have a functor of factorization categories, it induces a functor at the level of factorization modules for any given factorization algebra domain category. So here, I'll get a functor from factorization modules for this thing to factorization modules for this thing. This is just totally formal. It's just purely by functoriality, because this is compatible with factorization structure. And now we observe that this delta guy, not only is it the monoidal unit for this monoidal structure on the spherical category, it's also the factorization unit, also the unit for the factorization structure. Okay, and this is, again, just kind of comes from the way the factorization structure on the Hecke category is constructed. Like, if I think of the Grassmannian as a factorization space, the kind of factorization unit is sort of just, if you like, kind of the identity coset in the Grassmannian, right? And so correspondingly here. So this is actually just canonically equivalent to the spherical category itself. Okay. And now I claim this category is somehow more manageable than this endomorphism thing. even though like point-wise they're going to look the same, in fact, this category is somehow more manageable, and it's, well, for technical reasons, we have an easier time controlling it. So let me just quickly try to convince you that this category actually is sort of the category that you would want to see on the spectral side of derived Satake. So again, this was discussed a little bit last week. So A is a commutative algebra. It's a connective commutative algebra, for example, classical, like this one. Okay. Then it gives rise to a commutative factorization algebra by procedure explained in Frank's talk. And I could consider factorization modules for it. Let's say at a single point. And sorry, let me also write y for the spectrum of this algebra. It's connective. I can do it as functions on an affine scheme. So I can take factorization modules for this commutative algebra supported at a single point, and this is known to be equivalent to quasi-coherent sheaves on this horizontal loop space into Y. So if you don't remember what this is basically maps from the punctured disk from M into Y. So it's sort of horizontal maps from the punctured disk into Y. This was explained in Kevin's talk last week. The idea here somehow is that these factorization modules, like, I mean, these are related to just commutative modules. Just kind of just left modules over this commutative algebra. So any commutative module, just a usual left module, determines a factorization module. And so here, these are of course equivalent to quasi-coherent sheaves on Y, and Y I can think of as horizontal arcs, right? Somehow if I have an arc into Y and it's horizontal, it's just constant. These are just constant things. And so this maps to here by a direct image. So somehow when you allow a non-commutative factorization module structure, a general factorization module structure, you're allowing the maps that define the factorization module structure to acquire some poles, okay? And this corresponds to allowing these kind of arcs to acquire poles. Level of spaces. Okay, and then there's a relative version. So let's say now instead I have a map from Y to Z, which is affine. Okay, so I'm not assuming Y is affine anymore, but I'm assuming it's relatively affine over Z. Let's say Z is nice. For example, it could be a classifying stack. We'll actually apply it. And so then the kind of relative version here is if I take the direct image of the structure sheaf on Y, that's going to be a commutative algebra in quasi-co of Z. Okay. And I can take factorization modules for it as such. Back here. And this is going to be kind of the same procedure, but kind of relative. So this is equivalent to quasi-co of horizontal loops into Y, fiber product with horizontal loops into Z with horizontal arcs into Z. Okay. So it's horizontal loops into Y such that when I project to Z, they extend to an arc. Okay. Extend over the center. And so let's apply this in the derived Satake situation. Apply this in the derived Satake situation. So let's take y to be point mod g check and z to be Cartesian squared point mod g check. Okay. And so then what we get is the left-hand side is exactly this category, right? If I take the diagonal map for the classifying stack and I take the direct image of the structure sheaf, this is exactly the regular bimodule. Okay, so this tells me this category of factorization modules for the regular bimodule is equivalent to quasi-co of, now if you think about what this horizontal loops into the classifying stack is exactly local systems on the punctured disk, right? It's maps from the punctured disk into the classifying stack. That's a bundle, but they're horizontal, so they have a connection. So they're local systems. So again, to the extent that this is sort of heuristic, you run into these issues that we were asking about earlier about, how do you define local systems on the punctured disk? So you have to kind of deal with this somehow, but in any case, it can be made to work. All of this is kind of motivation anyway. So this gives you local systems on the local systems for G check on the punctured disk, fiber product over local systems for G check times G check on the punctured disk with local systems for G check times G check on the non-punctured disk. That's what I get if I just apply this formula here literally. This. I mean, this is what loops and arcs are. And I can rewrite this totally formally, right? This is the same thing as fiber product of locus G check on the disk with itself over locus G check on the disk. Okay. So this is kind of, now all of a sudden this looks much more kind of like what you would expect to see on the spectral side of geometric Satake, right? Because what appears on the automorphic side of geometric Satake? Well, the geometric object is this hecastack, right, which parameterizes two G bundles on the disk with an identification over the punctured disk. This is exactly the corresponding spectral gadget, right? I have two G check local systems on the disk together with an identification on the punctured disk. And instead of taking, on the automorphic side, we took D modules on the hecastack. On the spectral side, we'll take coherent sheaves. It looks very formally kind of analogous, just at the level of basic pattern matching. So that's sort of the first thing, the first like suggestion. Besides this conjecture, which I didn't probably do a good job of motivating, this is maybe a more explicit way of saying that this is the correct category to see on the spectral side. This is the spectral Satake category. Notice it, they say how naive Satake relates to this, right? So I think of G check as quasi-co locus on the non-punctured disk, right? That maps to this category. Let me call this category spherical G check spec. Okay. That maps to this category via just direct image along the diagonal. Right? And this is the functor that's supposed to correspond to naive Satake on the automorphic side. So what I've done, I guess, is I've constructed some version of the derived Satake functor. I've tried to motivate why the category that appears on the spectral side is sort of what one would expect to appear on the spectral side of derived Satake. And then there's still the question of, how to prove this functor is an equivalence to whatever extent it is an equivalence. There's still this business of renormalization, which I just kind of don't want to get into. I think it's probably not the best use of time. So how do I show the functor is an equivalence? Again, after this procedure of renormalization, I'll ignore. Okay, and here's sort of a sketch. And this is where actually ABG comes in at some point. Unfortunately, it's see what I can do with the time I have. All right. I ended up doing something kind of different than what I had anticipated. But on the other hand, if you go back and look at this version of the factorizable ABG equivalence that I wrote on the board near the beginning of the lecture, I stated it for a general parabolic, right? And I said for P equals B, I showed you how to recover the original ABG equivalence. Now, if you take P equals G, you get exactly this derived Satake thing. What I'm doing is I'm explaining the case P equals G. Okay. And somehow our proof proceeds by first writing down the functor for P equals G, then writing down the functor for a general P and relating it to that. Use this to prove that the functor is an equivalence in the case P equals G, and then we use that to prove that the functor is an equivalence for a general P. So there's this kind of seesaw logic going on. So this is somehow not too far in spirit from what we do anyway. Okay, so how do you actually show that this functor is an equivalence? Well, notice, okay, I have this naive Satake functor, rep G check to the spherical category, and it's not too hard to show that it has a continuous right adjoint. This is just saying that the Satake functor preserves compact objects, which is, well, up to, again, these kind of annoying renormalization issues is sort of trivial. It's just saying these things go to these IC sheaves, which are sort of have finite dimensional support, something like this. And so that kind of corresponds to the fact that the right adjoint is nice. It preserves colimits. The other thing is, in fact, these IC sheaves actually generate this category. That's also not too hard to see because the Schubert cells stratify the categories. So they're exactly, the IC sheaves on these orbits generate and some kind of, and so this right adjoint is also conservative. Left adjoint generates if and only if the right adjoint is conservative. Okay? And now that implies that spherical category is equivalent to modules over this monad. Check. Back. So in some sense, we can encode the spherical category in terms of some data in rep G check. Okay, and now there's a key calculation, which I believe is originally due to Ginsburg, which is that this monad is isomorphic to following algebra. So it's the symmetric algebra on the Lie algebra G check, And yes, it's G check, and it's viewed as an associative algebra in rep G check. So it's the simplest kind of monad is just an associative algebra. In fact, this one is an associative algebra, which is not too hard to see. It kind of follows formally from the fact that rep G check is rigid. And so I claim this monad is exactly just this associative algebra, very explicit, just this symmetric algebra. So this is this kind of equivariant cohomology calculation from one of Ginsburg's papers, 90 or so, right? And this exactly allows you to identify spherical category with modules for this symmetric algebra in rep G check. By the way, this is the equivalence that was proved in Bezer-Kadnikov and Finkelberg. So in some sense, it follows pretty formally from this calculation of works. But now, maybe I'll say for lack of time that on the spectral side, the spectral category will also be identified with the same module category for much more formal reasons. I mean, more formal because it just takes place entirely on the spectral side. So and here we have this renormalization issue. So for me to make this literally true, I would need to say int-co instead of quasi-co. I'll kind of ignore this. Just say on the spectral side, this category is also essentially equivalent to the same category of modules. This is quite formal from the fact that this spectral hecastack by the same kind of considerations I talked about at the beginning of the talk. This is equivalent to this fiber product, self-intersection of 0 inside of G check on G check. And so if you take the unit object inside of here, it's exactly kind of the skyscraper sheaf supported at 0. And endomorphisms of this thing relative to the action of rep G check is just formally is this symmetric algebra. Just the usual symmetric, like causal duality between symmetric and exterior algebras. Because the functions on this thing is sort of an exterior algebra, right? Sort of generated in degree -1. So endomorphisms of the augmentation module will be a symmetric algebra in degree 2. So you get this thing. And so what this tells us, right, is that the automorphic and spectral sides of derived Satake are abstractly equivalent, at least at a point, right? Without taking into account factorization structures. So that's very interesting. So just kind of, again, and this is just kind of what the content of the Bezer-Kadnikov-Finkelberg statement, if we take out the loop rotation stuff, right, which is more non-trivial. But if I ignore that, then that's kind of content of BF. But from here, it's not at all clear how to leverage this to prove that this functor is an equivalence. Because I've constructed this functor by some completely different means, right, than this identification. This identification was, well, it was using like this, which is something kind of special that you have when you fix a single point. Just totally unclear that the identification I get by composing this with this agrees with that functor, and there's really no reason for it to, because, like, for example, this functor is not even, this equivalence is not even really canonically defined. Remember, this uses a coordinate, for example. So it's just not clear at all. Okay. So what you do actually get, right, is this functor that we constructed. If I pass the endomorphisms of the unit object relative to rep G check, I'll get a homomorphism of associative algebras like so. Okay, and somehow, so it's very explicit, right? So like saying that this functor is an equivalence, again, because of the fact that naive Satake generates, is equivalent to saying that this map is an isomorphism of DG algebras. that seems extremely kind of checkable, right? Because in fact, this DG algebra is formal. I mean, it's concentrated entirely into, well, another way of saying it is just, I want to say that this map of DG algebras is a quasi-isomorphism. I can check at the level of cohomology. At the level of cohomology, again, it's just a symmetric algebra. And so this thing is commutative as a graded algebra even. So I can actually just check that it's an isomorphism on H2, right? That it's an isomorphism at the level of generators. Okay, this thing is even very formally equivariant with respect to the adjoint action. There's really not so many maps like this. And so the strategy is to show that the following is true. So again, I have this map, this endomorphism of the symmetric algebra that I'm trying to show as an isomorphism. Inside of here, I have the invariant subalgebra. I'll show that this is an isomorphism. That'll imply that this map is an isomorphism because the kind of invariants that sit in degree 2 generate the adjoint representation. So from the fact that this is equivariant, it's enough to show that this map is an isomorphism on invariance. Okay, so we do this by somehow, I have very little time now, so I have 15 minutes. Okay, so I can probably say something. So we do this by reducing to the case that G is torus. Which we can prove by other means. So actually, kind of, Valenson pointed out a long time ago that for a torus, we kind of know local geometric Langlands in just full detail. Like the kind of full conjecture that I stated earlier is literally true without the wavy equal sign for a torus, and you can give a completely explicit construction of the equivalence using a Fourier transform type construction. So there's still something to check here, which is that the way that we construct the Satake functor, that it actually agrees, like when I kind of pass to the Hecke categories, right, from sort of full local geometric Langlands, that it actually recovers like the same construction that I gave, but this is not too bad. So basically, and so this implies derived Satake for T in the form that I've constructed. And so we basically, now I just need to explain this reduction step. Okay, if you believe that for T, this is a known thing. Okay, and then the cool thing about the reduction step is it actually passes through ABG. So I'll explain the construction of the derived of the factorizable ABG functor. probably won't have time to explain why that's an equivalence, but at least you can see the construction and how it's used in the proof. Satake. Okay, so here's the construction of the factorizable ABG functor. I could do this for a general parabolic. Let me just do it for a Borel. I mean, from there, it's pretty easy to imagine how it would work for a general parabolic, and you'll see it kind of exactly interpolates between the case of a Borel that I'm about to say and the case of P equals G, which will recover the Gaitsgory construction. So here's kind of the opposite extreme. So what I'll do actually is I'll construct the functor from rep G check tensor. So the category that appears on the automorphic side of, let's see, do I want to do, I'm just going to write them in the other order. So the category that appears on the automorphic side of ABG is D modules on the Grassmannian, equivariant for loops n L plus T. I'll construct functor with this domain category. Okay, so first I'll use Castleman-Shaleka. Yes, it didn't matter which side I wrote it on because it's going to be annoying either way. So, okay, so these are both some categories of sheaves on the Grassmannian, right? So what I'm going to do is I'm going to invert, I guess, this factor, right? So it's instead of being L plus G invariance on the right, it's L plus G invariance on the left, and then I can convolve. Okay, so just again, because these are both categories of sheaves on the Grassmannian, there's a convolution operation. I convolve in the middle. Okay, and this is going to produce Whittaker category of E mod for G with the semi-infinite invariance thing, ln L plus T on the other side. And now this actually already appeared in Kevin's talk last week. So from here, it's going to be following in his footsteps. Okay, so where do we go from here? So this, then I forget the Whittaker condition. I just land in this, sorry, not for G, but loops G. Right, forget Whittaker on one side. Then I restrict to loops B. Okay, but now this is just loops T mod L plus T. In other words, it's GER-T. Okay, now D modules on GER-T is, for very straightforward reasons, equivalent to representations of T check. This is actually the G equals T case of Castleman-Shaleka. So that where the Whittaker condition is no condition, the torus. And so this is just, again, at a point, this is just saying GER-T is a disjoint union of points, the nilpotent stuff, indexed by the co-weights. So it exactly corresponds to getting a T check rate. Okay, so I've constructed a pairing from this ABG category tensor rep G check to rep T check. Okay. And this gives me a functor using the self-duality of rep G check. I can move it to the other side. let me just write it like this: G check times T check bimodules. So this is rep G check times rep T check, or I can write it as G check times T check bimodules. So this is just follows formally from that one by duality. Okay. So this is the upshot of this construction over here on the right two boards. Now, here I have the sort of standard object. It's like J lower shriek. So the shriek extension off of the neutral LN orbit. This is the unit for the factorization structure here. And one shows that this goes to certain factorization algebra. So it's exactly this R. So it's this thing that I'll call omega RG check. Okay, but this is kind of an obscure name for it. What it actually is R gamma of G check mod in check. So functions on G check mod in check. Where does this come from? Well, it comes from compatibility, something that was stated by Kevin last week, which is compatibility of Jacquet functors for these Whittaker categories. So let me not go into it, but say this is some calculation. Okay, it's non-trivial, but it's a calculation one carries out to show that this unit object here goes to this kind of interesting commutative algebra here of functions on G check mod in check. And here I really mean derived functions. So this is some DG algebra, like in degree 0, it's kind of a familiar thing. It would be like for SL2, it would be like polynomials of two variables, but then it has some higher cohomologies that are kind of nasty. Okay, and then if you want, you can define kind of the spectral side of ABG to be factorization modules for this thing. Or you can, by the same kind of considerations that I keep talking about, calculating factorization modules at a point, and show that this is the spectral ABG category. So at a point, this will be equivalent to this quasi-co of this guy. Same kind of calculation that I've done a couple of times. And this is spectral ABG category. So this is how we construct the ABG, spectral ABG functor. Right? The same kind of construction. Construct the functor of factorization categories, show the unit, calculate the image of the unit, which is going to be this commutative factorization algebra up there, and then its category of factorization modules will be in some incarnation of the category on the spectral side of ABG. In particular, at a point, they're the same category. This thing is, again, going to be kind of more manageable factorizably. And then, okay, so one can show this as an equivalence. The logic is a bit twisted. So in fact, like I said, the way that I'll do this is use this functor, first of all, to prove that the derived Satake functor is an equivalence. And then you combine derived Satake with the factorizable ABE equivalence from Kevin's talk last week to prove that factorizable ABG is an equivalence. So again, it's a bit of like seesaw there with the logic. But let me just at least try to explain this reduction step here. So I'm 4 minutes left. I think I can do it. Let me introduce notations for the ABG categories because they're just way too cumbersome to keep writing over and over again, right? So I'll call this category SFA, G check, comma B check, spec. It's a reasonably logical name, and then I'll call this SFA G comma B. Sense. So then we get a diagram. So up here, I'll have derived Satake. Down here, I'll have derived Satake for T. Here, I'll have the ABG category, spectral one. And I'll have this factorizable ABG functor that I constructed. And now, the thing about the ABG categories is they're bimodules for the spherical category for G and for T. Right? I mean, look at the here, has invariance for L plus G, something on the Grassmannian, and invariance for L plus T. Right? So it's acted on by SVA G and SVA G. And then similarly for the spectral category, well, you can, in fact, see it for this factorization module version using the way that I wrote down the spectral category, spectral Hecke categories for G-check and T-check. But let me just say this is believable. So in particular, I get functors like so, where I just act on the kind of unit object here, right? So these are similarly over here, acting on the unit object in this bimodule. Okay. Now, all of these functors send unit objects to unit objects, right? The horizontal functors, I mean, all of them by construction send unit objects to unit objects. And so I'm going to pass to endomorphisms of the unit object. Okay, for all of these categories, and I get a diagram PG algebras. So endomorphisms of the unit in the Hecke category, in the spherical Hecke category, is the symmetric algebra, but G-check invariance, because I'm just taking endomorphisms of the unit. So this actually is just the Chen-Bay isomorphism. It's endomorphisms of the delta thing in something that's G equivariant, right? Is equivariant cohomology of G. And that's exactly this via Chen-Bay. So the calculation of Ginsburg that I mentioned earlier is kind of an equivariant upgrade of this. And likewise, on the spectral side, it's the same, sort of for more tautological reasons. And then here, endomorphisms of the unit object in the ABG category is just the symmetric algebra of T-check shifted by -2, because it's just equivariant cohomology for T. Again, it's Chen-Bay. And over here, you'll get the same thing for more tautological metric reasons. And then down here in the spherical category for T, of course, it's the same because T-check invariance here doesn't do anything. Okay, and so it's easy to see these functors are the identity. This is the inclusion via the Chevrolet map, right? Because this is sem of T-check shifted by -2 to W invariance, right? Likewise over here. And so, as I said, if we believe in derived Satake for a torus, this is an isomorphism. Therefore, this is an isomorphism. Therefore, this is injective. And that's enough. Because actually, and I didn't mention this earlier, but I'm also going to use the fact that the adjoint representation of G-check is finite dimensional. Okay. The fact that this is injective on G-check invariance and the fact that G-check invariance generate under the adjoint action in the H2 of sim G-check tells me that in fact this is enough. That's the proof.
Sorry. So the bottom line is that this one is going to be an isomorphism, or this will stay injective the top line, top horizontal arrow.
Top horizontal arrow. So I'm saying what this, the fact that this and therefore this is an isomorphism just implies this is injective.
Yes.
And I'm saying that's enough. I mean, if it's injective, of course, it's an isomorphism. Isomorphism.
Oh yeah, this is fine.
The cohomologies are finite dimensional. Okay.
This one.
So sorry, I should have said, yeah. So this is an isomorphism, therefore this is an isomorphism, therefore the top arrow is injective. Because the cohomologies are finite dimensional, it's therefore an isomorphism. And as I explained earlier, that implies that you get an isomorphism even without taking G-check invariance. And that applies for Satake. Okay, I'll stop. That's for questions? Yeah.
Notation.
Yes.
What's that? Organo mod, and then you bracket rep. At the very top.
Oh yeah. Here. So functions on G-check mod in-check is a bimodule for G-check and T-check. G-check acts on the left and T-check acts on the right.
Functions on, yeah.
So G-check mod in-check is acted on by the left by G-check and on the right by T-check. Therefore, its algebra of functions is a bimodule for G-check mod T-check. T-check. And it's a commutative algebra as such. Right? It's a commutative algebra and it's equivariant for G-check times T-check. And so I can therefore take factorization modules in this ambient symmetric monodal category.
As a category. What are the objects? Sorry.
The objects in here. So it's an object of a bimodule for G-check, T-check. Yeah. Together with a factorization module structure for this commutative algebra that's compatible with the bimodule structure, with the structure of representation of G-check times T-check. So it's just a general thing, right? Like if I have an associative algebra in a symmetric monodal category, I can consider bimodules for that associative algebra in that ambient category. Just for some total abstract nonsense reasons. And this is the analog of that, but for factorization modules instead of bimodules. So it's quite analogous. So I mean, I could try to say explicitly what they are, but I think it would be kind of useless because I think it's better to just think about the case of like, if I have a generic factorization algebra, okay, there's this category of factorization modules at a point, and you should first try to kind of understand what this is. And this is some just generalization of this with declarations. Okay, so conceptually, it's kind of going on here. Just what is a factorization module? It was discussed 2 weeks ago, which unfortunately was not recorded either. And this is just the same thing, but kind of with this extra decoration of having a G-check and T-check action go along for the ride. And again, this is some kind of fancy incarnation of this category that appears in ABG on the spectral side. It's coherent sheaves on the derived Springer fiber. Yep. So again, the logic is kind of funny because I use this construction of the ABG functor, but I didn't yet prove that it was an equivalence, but I didn't need to. So it was enough to kind of know that it induces an isomorphism on endomorphism of the unit object, which followed from the derived Satake for T, and that enabled me to deduce derived Satake. And then you have to prove the factorizable ABG by some other means. So again, the way that it's proved both in my paper with Sam and in GLC3, very close, very similar proofs, is you combine derived Satake for G and this factorizable AB equivalence, and somehow those together are enough to imply that this functor is an equivalence. Somehow, because if you know it, so the AB was similar, but instead of having kind of a spherical condition with respect to G, you had the Whittaker condition, right? But somehow, if you know the equivalence on Whittaker, you know it on spherical category as well, as long as you know derived Satake. So somehow you get other questions? Be on Zoom.
Thank you very much.
All right, stop there.